The Fundamental Theorem of Calculus, Part 2. Before we look at the formal statement of the Fundamental Theorem of Calculus, Part 2, we have to define an area function. So we're going to go ahead and define a of x to be equal to the integral from a to x of f of t dt, and that's going to represent the signed area from a to x. So here we have this definite integral, where here we're being told that a has to be a real number. So the lower limit of integration has to be a real number. X is the variable of the area function. So the area function has this independent variable x. We're going to be substituting in values for x. And t here is considered a dummy variable. So that'll make a little bit more sense if we take a look at this example. So we're going to let a of x be an area function defined by the integral from -1 to x of f of t dt. So far I've met the specifications. I have a is a real number as a lower limit of integration. I have x, the independent variable of the area function, in the upper limit of integration spot. And I'm evaluating a definite integral of the function f. So what I mean by a dummy variable is that this function here that we're going to be looking at to evaluate our definite integral is called the function f of x, really. But we don't want to make it confusing because x is the independent variable of the area function. So instead of calling f of x in this integral, we're going to go ahead and call it f of t. So remember that a function is it could be interchangeably used with all kinds of different variables as long as we stay consistent. So we could have called this f of theta, we can call it f of heart, it really doesn't matter. No matter what, it's still f. So that's the part that I can't change. It's still the function f. So I want to be able to understand this area function. So real quick, let's just revisit a very familiar function. So let's say we have f of x equals x squared. So just as a quick reminder of functions, remember that we can substitute in a value for x, and we have to get out exactly one y value. So let's say we plug 2 in for x, we get 2 squared, and 2 squared is 4. So when we substitute in 2, we get out a y value of 4. So we could not get out two different values, otherwise we would not have a function. Let's say we substitute in -2. So -2 squared is still positive 4. So it's possible for two different x values to go to the same y value, but I need only get out one value when I plug in a particular x value. So just as a reminder about functions, and this area function here is going to be a function just like something like x squared that we're familiar with. And then just to kind of tell you where we're headed, when we have a function, we want to be able to describe properties about that function. So we want to describe whether it's increasing or decreasing or concave up, concave down, and for that we need to be able to take the derivative of it. So let's first try to really understand this idea of an area function, and then we're going to think or find out how this area function, even though it doesn't look like it, is really just something as simple as x squared. And then once we are concrete on that idea, we can then explore taking its derivative and describing its properties. So here's my area function, the integral from -1 to x of f of t dt. So let's evaluate a of 0. A of 0 is going to be the integral from -1 to, again substituting 0 in for this x, so the integral from -1 to 0 of f of t dt. So I'm going to reference the graph, and that's going to give me the integral from -1 to 0, so the signed area between the curve and the x-axis. Well, that's this nice geometric shape of a rectangle. So if I want to find the definite integral, it's going to be negative because this is below the x-axis, and the area of a rectangle is base times height, so the base is 1 and the height is 2. So I'm going to have -1 times 2, or just -2. So right now it's looking pretty good that a of x, even though it looks like this integral, is really just a function. I substituted in 0 and I got out one value that was a number, and that number is -2. So now let's evaluate a of 2. So I have the integral from -1 to 2 of f of t dt. So that's saying I want to find all of the area between the curve f of x and the x-axis between -1 and going all the way out to 2 this time. So I want all the area here below the x-axis. Well, let's not make my life any harder. I've already found that this area here is -2. So far I'm going to have -2, and I'm going to add more negative area. So this triangle is below the x-axis as well. So the area of this triangle is 1/2, the base is 2, and the height is 2. So 1/2 times 2 times 2. So what I'm going to end up with is -2 plus this part right here will also be -2, so I'll end up with -4. So by looking, I can tell that so far this portion here was also -2, so I should have an all negative area because I've so far only added up area below the x-axis. But now I'm going to go all the way out to a value of 6 for the next one. So I want the integral from -1 to 6 of f of t dt. So that's going to equal, well, I have all this negative area here already, so I'm going to go ahead and include that, but now I'm going to start adding positive area. So all the way from 2 to 6, I'm going to go up to the function, and I need to add all of this positive area up here that forms the shape of another triangle. So the area of this triangle is 1/2. Between 2 and 6, I have a base of 4 and a height of 4. So now here I have 16 times 1/2 is 8. Positive 8 plus -4 is going to give me a +4. So it does look like there's more positive area up here than there is negative area down here. So my answer for a of 6 should be a positive number, and we got out +4. So now let's take a look at a of -4. So I'm going to plug -4 into this x, so I'll get the integral from -1 to -4 of f of t dt. And here we arrive at a different result. So here I have -1 to -4, so I normally want a smaller number to a bigger number, and -4 is the smaller one and it's on top. So if I want to switch the limits of integration, I have to put a negative in front. So I have to do negative the integral from -4 to -1 of f of t dt. So now I'm looking at the integral from -4 to -1, and that's going to be negative area because it's below the x-axis, but then there's this negative in front also. So it's going to be negative. The base of this rectangle is 3 and the height is 2. So 3 times 2. So I'm going to end up with +6. So between -4 and -1, you might be thinking, well, it's below the x-axis, but because the limits of integration were from bigger to smaller instead of smaller to bigger, that's what ended up making the final answer here being a positive number. And so now let's move on to the next example. Oop, and this is a typo. This is supposed to be a of -1. Sorry about that. So a of -1, here, if I go in and substitute -1 into the upper limit of integration, I'm really going nowhere. So this was a property of definite integrals. If I go from a to a, then I have no width to my rectangle or any type of shape at all. So this is just 0. So it's possible to get out no area at all. I can get out negative answers, positive answers, just like any other function. So this area function here is going to be a building block to understanding the fundamental theorem of calculus part 2. Alright, so we've decided that a of x, which is the area function from little a to x of f of t dt, is a function, and we refer to it, in addition to an area function, as an accumulation function, because if you notice that as we moved along, we kept accumulating more and more area the further we went. So that's another name for an area function, is an accumulation function. Now, in general, as I mentioned briefly before, when we have a function, we want to be able to describe its properties. So when we had x squared, we want to be able to describe what it looks like, where it's increasing, where it's decreasing, where it's concave up, where it's concave down. And to do that, we went through a whole chapter on derivatives, where we can use the properties of derivatives to help us describe the original function. So if you remember, if the derivative of a function is positive, then the original function is increasing. So we want to describe the properties of this area function, such as its monotonicity, its extreme values, etc. And to do so, we need to be able to find the derivative of a of x. So we're going to have this area function, which is uniquely defined. We haven't seen something like this before, as an area function written as an integral. But if we have a function, we should be able to take its derivative. And the fundamental theorem of calculus part 2 is going to help us with that. So we're going to go over an example that allows us to explicitly find a formula for the area function a of x equals the integral from 3 to x of t squared dt. Let's go ahead and rewrite the problem. So we have a of x equals the integral of 3 to x of t squared dt. So right now, what we can do is we can apply the fundamental theorem of calculus part 1. So we have this definite integral from 3 to x, but remember x stands for some real number. So a definite integral goes from a number to a number, but since x represents a number, we can go ahead and apply the fundamental theorem of calculus part 1. So let's take the antiderivative of t squared. So that's going to be t cubed over 3. And we're going to evaluate this from 3 to x. So the same process with the FTC part 1, except we're moving on with the x as a variable instead of as a real number because it stands for a real number. So now we're going to move on. We're going to substitute the x in, the upper limit of integration first. So we're going to have x cubed over 3 minus, if I substitute in 3, I'm going to have 3 cubed over 3. So now I can simplify this. I have 1/3 x cubed minus, I have 27 divided by 3, so 9. So what I started out with was a of x equals 1/3 x cubed minus 9. So let's rewrite that over here. A of x equals 1/3 x cubed minus 9. So the problem asks us to find a formula for the area function a of x equals the integral from 3 to x of t squared dt. So we've done it. We found an explicit formula to do this. So let's go back to the area function real quick. So if I have this function, t squared or x squared, right, because it's a dummy variable, and I want to think about what's happening from 3 to x, where x is some value bigger than 3 because it's above, it's the top limit of integration. So let's say I wanted to find the area from 3 to 4. Whoops. Not 3 to 3, 3 to 4. So if I wanted to find the area from 3 to 4, well, I could go ahead and plug 4 into this upper limit of integration, and that would tell me the integral from 3 to 4 of t squared dt. But I found an explicit formula for it. I found that the area, no matter what, from 3 to some number bigger than 3 can always be found by plugging that number bigger than 3 into this explicit area function. So if I want a of 4, well, I can just go ahead and plug 4 into this x. So 4 cubed minus 9. So here I'm going to have 64 divided by 3 minus 9. And we don't need to simplify any further. That would be the area. So what I had mentioned previously was that we were going to try to describe this area function. So this area function isn't typical, right? It looks like an integral, but what we did was we took it down to a function that's recognizable. So, and more importantly, a function that I can easily take the derivative of. So if this is a of x, a prime of x, well, this is just a polynomial. I can apply the power rule. If I bring this 3 to the front, 3 times 1/3 is 1. And then I'm going to have x to the, reduce the power by 1, x squared. And then the derivative of 9, or any constant, is 0. So I started out with this area function. A of x equals the integral from 3 to x of t squared dt. Well, it turns out that exact same thing equals 1/3 x cubed minus 9. Well, now, the idea was we wanted to be able to take the derivative of a of x. Well, in this form here, I don't know how to take the derivative of something that looks like this, but I do know how to take the derivative of something that looks like this polynomial, and I did. I got x squared. But what I want to point your attention to is x squared and the integrand of the original area function, t squared. So they're the same function, just different by a variable. And I want you to keep that in mind as we look at the actual fundamental theorem of calculus part 2. The fundamental theorem of calculus part 2. Let f of x be a continuous function on AB. Then, a of x equals the integral from little a to x of f of t dt is an antiderivative of little f of x. Or a prime of x equals f of x. Or, and here's the most common one we're going to be using, the derivative with respect to x of this area function, the integral from a to x of little f of t dt, is the exact same thing as f of x. So a has to be a real number. And then we're also being told that a of x satisfies the initial condition a of little a equals 0. So what's happening here is that if I take the derivative of an integral, I get out the integrand, the original function. So if you notice what's kind of happening here is this x is going right there into that dummy variable. And it doesn't matter at all what the lower limit of integration is, provided that it's a real number. Because if we think back to that previous example, that -9 that was the constant at the end of the a of x, the area function, when I took its derivative, the derivative of a constant is 0. So that's why this lower limit of integration doesn't really matter. So here we're just concerned that we're taking the derivative with respect to x of an area function where x is in the upper limit of integration, a number is in the lower limit of integration, and we just take that x and substitute it into the dummy variable, and that's our answer. So we don't take the derivative of f, we don't take the antiderivative of f, it's just f of x. So let's try to look at an example. Alright, let's take a look at an example. It's telling us to find the derivative of a of x, this area function, from 4 to x of the square root of 1 plus t cubed dt, and then evaluate a prime of 2 and a prime of 3. So we're trying to find the derivative of this area function. So the derivative with respect to x of the integral of 4 to x of the square root of 1 plus t cubed dt. Now, just to kind of parallel it with what we did earlier, we were trying to find the explicit formula for the area function given by the integral from 3 to x of t squared dt. And this was something we were able to do. We were able to explicitly find the formula for this. So we were able to say that this is the same as t cubed over 3, just as a quick reminder, from 3 to x. And this was the same as x cubed over 3 minus 3 cubed over 3. And then if we wanted to take the derivative, well, this was a of x. So a prime of x is taking the derivative of this function, which we got out to be x squared. So notice that what we could have done was, well, we're taking the derivative with respect to x of the integral of 3 to x of t squared dt. The fundamental theorem says that what I can do is, since I'm taking the derivative with respect to x of an area function where a number is on the bottom and the variable x is the upper limit of integration, I just take this x and I plug it into this t, and that's my answer, x squared, which is the same thing I got by finding an explicit formula for the area function. Alright, so that's just a quick recap of what we did in the previous example. Now here, we have no choice but to use the fundamental theorem of calculus part 2, because I can't even find an explicit formula for this as a general antiderivative. There's no way that I can find the general antiderivative of the square root of 1 plus t cubed. I don't have a formula for that. Here, we had the power rule for integrals, but here, I don't have any such formula. So this is a direct application of the FTC part 2. I take this x here, and I substitute it into this t, and that's my answer, the square root of 1 plus x cubed. And that's it, I'm done. There's no plus c. Why is there no plus c? Because I'm taking a derivative. Never have I ever before put a plus c on a derivative. That's on an antiderivative or a general antiderivative. So fundamental theorem part 2, if I have a derivative of an area function with an upper limit of integration as an x and the lower limit to some number, I just take that x and plug it into the dummy variable of the integrand, and that's my answer. So now, that was the first part, find the derivative. Well, here it is, the square root of 1 plus x cubed. And now evaluate a prime of 2 and a prime of 3. So what we just found here was a prime of x, so a prime of 2 is the square root of 1 plus 2 cubed. 2 cubed is 8, plus 1 is 9, so the square root of 9 is 3. And then find a prime of 3. So I'll get the square root of 1 plus 3 cubed. 3 cubed is 27, plus 1 is 28, so the square root of 28. I can simplify that to 2 radical 7. So the first part was finding a derivative of an area function, and that's a direct application of the FTC part 2. And then once you find that derivative, we can substitute in numbers. So the first one was the whole number 3, and then the second answer, 2 radical 7. And now for 2 more examples. So if I want to evaluate the derivative with respect to x of the area function from 4 to x of sine t squared dt. So again, I have a derivative of an area function where an x is in the upper limit of integration. So I take this x, I substitute it into t. So my answer here is sine x squared. And that's it. I just plug the x into the dummy variable. I don't take the derivative of sine. I don't attempt to take the antiderivative of sine. It's just sine of x squared. And again, no constant because there's no constants when I take derivatives. So now let's evaluate the derivative with respect to x of the integral from x to 3 of e to the t dt. This one's a little different. So if I want to flip the limits of integration, I have to make sure and include a negative. So I'm taking the derivative of negative the integral from 3 to x of e to the t dt. Well, now my properties of derivatives say that I can pull a constant like negative 1 out of any derivative. So I'm finding negative the derivative with respect to x of the integral from 3 to x of e to the t dt. And now I have the perfect situation to use the FTC part 2. So I take this x, plug it into t, and I get negative, because of this negative here, e to the x. And that's it for this problem. Alright, so what's taking a derivative without using the chain rule? So here, the fundamental theorem of calculus part 2 has a second portion to it that involves using the chain rule, because ultimately we're taking a derivative. So the derivative with respect to x of the integral from a to g of x. So now, instead of just x, it's some function g of x of f of t dt equals f of g of x. So we're going to take that g of x, what's in the upper limit of integration, plug it into the function f, and then multiply by the derivative of the inside being g of x, so we multiply by g prime of x. And again, a has to be a real number. So the fundamental theorem of calculus part 2 has a second part to it, an extended portion that allows us to use the chain rule since we're taking a derivative. So let's go ahead and evaluate this problem. I have the derivative with respect to x of the integral from negative 2 to x squared of natural log of t dt. So this one's different. It's not just an upper limit of x, it's a function x squared. So I take x squared and I plug it into this dummy variable t. So it's going to be the natural log of x squared. But now I multiply by the derivative of the inside, or the derivative of the upper limit of integration. So the derivative of x squared is 2x. So my final answer here is going to be 2x, the natural log of x squared. So that is applying the fundamental theorem with the chain rule. So if the upper limit of integration is a function of x, I have to remember to use the chain rule. Let's take a look at another example. I have the derivative with respect to x of the integral from negative 2 to cosine x of sine t dt. So now what I want to do is take the cosine function and plug it into the dummy variable t. So this is going to be a chain rule. I have a function of x in the upper limit of integration. So I'm going to have sine of cosine x times the derivative of cosine x is negative sine x. So I'm going to have negative sine x times sine of cosine x. So we want to make sure not to sneak an extra x in here. And remember, I'm plugging cosine x into that t. And then here I want to be careful to either write negative sine x in the front Or be sure to include parentheses here, because if these parentheses were not here, it would look like minus sine x, and that's not the case. So this is going to be the final answer here. And now, this next example, evaluate the derivative with respect to x of the integral from x to e to the x of the square root of t dt. So this one's really different. I have variables and functions, well, functions of x, in both the lower and upper limit of integration. So to solve this problem, what I need to do is figure out a point that I want to break this integral up into. So what I want to do is rewrite this as the derivative with respect to x of the integral from x to some number of the square root of t dt plus the integral from that same number to e to the x of the square root of t dt. The question is, what number do we choose? But the real question is, does it even matter? And the answer is no, it doesn't matter. If I want, I can call it just some other constant. I can call it k, I can make it pi, I can make it really anything I want. So just to make it easy, let's make it 0. Because remember, the constant, like this -2, never mattered at all. So as long as it's a real number, it doesn't matter. So if you're going to call it k, as long as you remember k stands for a real number, that's fine. So here I'm rewriting this as the integral from x to 0 of the square root of t dt plus the integral from 0 to the e to the x of the square root of t dt. So now derivative properties tell me that I can take the derivative of each one of these independently. So I can take the derivative with respect to x of the integral of, I'm going to do a couple of things at once here. These limits of integration need to be flipped, so I need the x on the top. So I'm going to have 0 to x, but that will make this negative, of the square root of t dt, plus this derivative will come and apply to this area function, and the integral from 0 to e to the x of the square root of t dt. So now here I have negative, and here I only have an x in the upper limit of integration, so I can just plug this x in for t. So I have radical x. And here, even if I applied the chain rule, well, the derivative of the inside is just 1, so I'm done here. Plus, now I plug e to the x into this t, so I have the square root of e to the x, but this is a function of x, so I need to multiply by the derivative of e to the x, which is e to the x. So now here, if I want to simplify, I can write this as negative the square root of x plus, this would really be e to the 1/2 x times e to the x. And then if I wanted to simplify more, I can write this as negative radical x plus e to the, and here I would be adding those exponents, so a 1/2 x plus x is going to be 3/2x. I could write this, whoops, as my final answer here. Let's stop for a second and see a huge connection here. So the fundamental theorem of calculus part 1 says that the integral of a derivative gives us the original function. So if I take the definite integral from a to b of big F prime of x dx, I get out the original function f evaluated at the limits of integration. So the integral of a derivative, they sort of cancel each other out, and I get to the original function f. Now we've explored the fundamental theorem of calculus part 2, which says that the derivative of an integral gives us the original function. So I have the derivative with respect to x of an integral, and what happened was the derivative and the integral cancel out, and I end up with just f of x. So the derivative and the integral have an inverse relationship here. That's the connection. So they sort of cancel each other out in the sense that when I have an integral in front of a derivative, I end up with the original function. If I have a derivative in front of an integral, I end up with the original function. So that's the big connection. That's what relates derivatives and integrals, and it is the fundamental theorem of calculus. So you can imagine its importance if it's called the fundamental theorem. So now let's look at some assorted AP multiple choice questions. So the derivative with respect to x of this area function, well, I have a number in the lower limit a variable x in the upper limit that matches the derivative with respect to, so I can just plug this x into this t. So my answer is going to be the square root of 1 plus x squared, and the only option that has that is C. So these aren't meant to be very long questions as long as you recognize the form. So when I see a derivative in front of an integral, I should think the fundamental theorem of calculus part 2. So let's take a look at another example. In this next example, I have big F of x equals the integral from 1 to x squared of the square root of 1 plus t cubed dt. And I'm being asked to find f prime of x. So I have an integral that's an area function, and I'm being asked to find its derivative. So I should think, again, fundamental theorem part 2. So here, I'm finding the derivative with respect to x of the integral from 1 to x squared of the square root of 1 plus t cubed dt. So this is the special case of the chain rule with FTC part 2. So I'm going to take this function, x squared, and plug it into the integrand. So I'm going to get the square root of 1 plus x squared cubed. So I need to plug in x squared for t, times the derivative of the inside. The derivative of x squared is 2x. So now let's go ahead and simplify. We'll put the 2x in the front and we get the square root of 1 plus, here I have x squared cubed, so we multiply these, so I have 1 plus x to the 6th underneath the radical. So 2x times the square root of 1 plus x to the 6th, and that's going to give us answer A. And now it's time to look at a free response question. So this is the 2005 AB free response question from Form B. And we're going to be going over a lot of these types of questions. This type of question appears so frequently on the AP free response portion of the test. So here's this graph of f, and we're told the graph of f above consists of 3 line segments. And in part A, they're asking us to let g be the function given by g of x equals the integral from -4 to x of f of t dt. For each of g of -1, g prime of -1, and g double prime of -1, find the value or state that it does not exist. So let's go ahead and start working this problem off to the side. So what we're going to do first is try to evaluate g of -1. So here's the g of x function. G of x is the integral from -4 to x, so it would be from -4 to -1 of f of t dt. Well, here's -4 and here's -1, so I'm being asked to find this area here. So if I want, I can break it up into a rectangle and a triangle, or I can find the area of a trapezoid. So I'm going to find the area of a trapezoid. So the area of a trapezoid is 1/2 the height. So the height in this case is going to be right here along the x-axis, so 1, 2, 3 units. And then base 1, so base 1 here will be 4, and base 2 here is going to be 2, so we're going to have 4 plus 2. And then since all of this area is below the x-axis, I can't forget to make the answer negative. So 4 plus 2 is 6, 6 times 1/2 is 3, 3 times 3 is 9, so g of -1 is -9. So I found g of -1. And now we need to find g prime of -1. So here's the big connection that we're going to use throughout the problem. If g of x is the integral from -4 to x of f of t dt, then g prime of x, well, I'm taking the derivative of this integral. G prime of x means I'm going to plug this x into this t. So g prime of x is the same as f of x. So this graph here that's been given, this graph is the graph of f, but we just said f is the same as g prime of x. So what I'm going to do to remind myself is label this graph. This is the graph of f, but f equals g prime. So this graph represents two things. It represents f and it represents g prime. So with that in mind, we're going to let g be this function, and we're trying to find g prime of -1. Well, if this is the graph of g prime, if I want g prime of -1, well, here's -1. I'm just simply looking for the output value. So the output value here is -2. So this coordinate point is what I'm interested in. So g prime of -1 is -2. And then g double prime of -1, well, let's go back over here to this relationship. If g prime of x equals f of x, then g double prime of x equals f prime of x. So if I'm trying to find g double prime of -1, that's the same as trying to find f prime of -1. Well, here's the graph of f. If I want f prime of -1, I want the slope of the tangent line at -1. Well, what happens there is a sharp turn or a cusp. So what do I know about f prime of -1? It does not exist. So when they gave you this piece of information, they asked you to find three different things: g of -1, g prime of -1, and g double prime of -1 if possible. If not, state that it does not exist. So the answers here are -9, -2, and does not exist. Alright, so now let's look at part B. For the function defined in part A, find the x-coordinate of each point of inflection of the graph of g on the open interval from -4 to 3, and then explain your reasoning. So we want to figure out on the graph of g the different x-coordinates of the points of inflection. So in order to find points of inflection on the graph of the first derivative, so we also know that g prime of x equals f of x. So we can use the second derivative, of course, but we have exactly the graph of the first derivative. So this graph here of the first derivative of g, we know that inflection points occur on the graph of a derivative when the derivative changes from either increasing to decreasing or decreasing to increasing. So on this graph of g prime, if we want to know when does g have points of inflection, well, from -4 all the way to 1, this function is increasing, and then from 1 to 3, this function is decreasing. So g prime changes from increasing to decreasing at 1, which means that g changes from concave up to concave down at 1, which makes the x-coordinate 1 a point of inflection. So here, find the x-coordinate. The x-coordinate is x equals 1, since f equals g prime, and g prime changes from increasing to decreasing at x equals 1. So that's enough of an explanation. F equals g prime is necessary, and then letting the reader know that g prime changes from increasing to decreasing at x equals 1 tells us that x equals 1 is going to be a point of inflection on the graph of g. So now for part C. Let h be the function given by h of x equals the integral from x to 3 of f of t dt. Find all the values of x in the closed interval from -4 to 3 for which h of 0 or h of x equals 0. So this one is a little bit tricky, I would say. So here's what we have. We have h of x. We're given a new area function from x to 3 of f of t dt. So what we're used to having for 1 is the lower limit of integration being the number. So how about we write this as h of x equals negative the integral from 3 to x of f of t dt. So what we're being asked is what values of x. So what values can I plug in here into this x here such that the answer will give me 0? So for 1, this negative doesn't really matter because I want to get out an answer of 0. And I'm thinking about what x values can I plug in that will give me an integral, that will give me an area, a signed area of 0. Well, the very first option is going to be 3. If I substitute in an x value of 3, so h of 3 equals negative the integral from 3 to 3 of f of t dt, well, if the limits of integration are the same, my output is 0. So automatically I know that x equals 3 is one of the options. So x equals 3. But now, let's go ahead and erase that for more space. Now I want to think about what other options might give me an area of 0? So notice here I want this area function from 3 to x. So here's this x coordinate of 3, and my values of x are going to have to be smaller than 3. So they're going to have to be going in this direction because I don't know anything about what's going on to the right. So let's say between 3 and 2. So between 3 and 2, I know I'm going to have this area here, which would normally be negative, but because we're going in a reverse direction, it's going to be positive. But then this negative here is going to make it negative again. So either way, though, it's some answer that's not 0. But if I keep going, so if I go all the way to 1, so now I'm going to have this area down here, and I'm going to add to it this area here. So one of these areas is positive and the other is negative. So they notice they're the exact same area, and one's above and one's below. So regardless of which is positive and which is negative, they're going to cancel each other out. So that happens when I go from 3 all the way to 1. So that means the other value that will make this integral 0 is, positive 1. And then I could try to see if it will work if I go any further. So if I keep going, if I keep accumulating more area, well, now I have more positive area than negative area. So this isn't going to be 0. But if I keep going and I stop right here at negative 1, well, now this portion cancels with this one. So this upper triangle cancels with this lower triangle, and this upper triangle cancels with this lower triangle. So also at a value of negative 1, am I going to have an area function that yields an area of 0? Because I have some symmetry here happening. So I have the same shape on top, exact same shape on top as on the bottom, and that's going to happen twice as I move along from 3 and I head to the left. But if you notice, if I keep going, I'm just going to keep putting more and more area that's below the x-axis, and I have nothing to counter it with anything above. So negative 1 is the only option that we have that will work from then on. So our three answers here for part C are 3, 1, and negative 1. Now for part D, for the function h defined in part C, find all the intervals on which h is decreasing. Explain your reasoning. So in order to determine when a function is decreasing, we would want to know when its derivative is negative. So now let's go ahead and try to find h prime of x. So here I'd be using the fundamental theorem of calculus part 2 again. So if I want to take the derivative, well, there's still going to be that negative there, but the derivative is going to have me put this x into t. So h of x, or h prime of x, is equal to negative f of x. So now what I would need to do is figure out, well, when is h prime of x less than 0? Well, that's the same as asking when is negative f of x less than 0. So the graph shown here is f of x, not negative f of x. So now, negative f of x, what does it mean to put a negative in front of a function? Well, what it's going to do is it's going to reflect the entire function over the x-axis. So let's go ahead and erase what we have. So this function here is the graph of f. So the graph of negative f of x is going to flip everything. So this portion that's down here is going to flip to up here. And this part up here is going to flip and move down here. And then this line will be the mirror image over the x-axis. And then finally this point here will also reflect and go all the way out to 4. So now this new graph that I've drawn is the graph of negative f of x. So on what intervals is this graph here, this negative f of x graph, whereas this graph negative? I want to know, when is this graph below the x-axis? Well, that's going to happen on the interval from 0 to 2. So the answer here, sorry I ran out of space, is going to be from 0 to 2, since, and you're going to write out basically the work that you did over here, since h prime of x equals negative f of x, and negative f of x is less than 0 on 0 to 2 is going to be the explanation.